Hello everyone, my name is Yuhei Takahashi, and I am a PhD student at Osha University in Japan. I'd like to talk about asymptotic analysis of coded slotted ALOHA. In my presentation, after describing the problem, I'm going to give derivations of belief propagation threshold, converse band, and map threshold of coded slotted ALOHA system over Rayleigh channel. Finally, I'll present some numerical results. We call the massive sensor network. In the network, there are huge number of NT devices transmitting their packet to a common access point. All devices are equipped with a common channel code and segment-oriented code set. Each device generates a single message with activation probability pi. In other words, at one instance, only a part of devices become active. We adapt the well-known coded slotted ALOHA system, ALOHA protocol, one of the random access protocol, to the network. Here, I focus on a single device. Each device has a single message to be sent. We encode the message using segment-oriented encoding and channel-oriented encoding. Specifically, we partition the message into k equal length message segments. Then we encode these k segments by appending U parity check segments. This k-dimensional code is linear and systematic with code length k plus U. In our work, the code is maximum distance separable code. With channel-oriented encoding, we further encode each segment by channel code with rate R and send to access point over Rayleigh channel. Since there exist interference from other active devices, phasing, and noise. First, the active access point tries to decode each segment with threshold-based decoding. Some segments may be failed in the channel decoding. Thanks to the maximum distance separable code, we can recover k-message segment if at most n-k segments are erasured. Therefore, the original message can be received correctly. Let's describe the coded slotted ALOHA protocol. Each active device has a single message to be sent within a frame of m slots. Each slot is divided to k slice slots. An active device randomly chooses a constituted code from segment-oriented code set with probability lambda nu. The device encodes its message using previously described method and sends its nu coded segments over nu slice slots randomly among the k times m slice slots. The average code rate of segment-oriented code is also called energy efficiency. The set of lambda n is a device distribution. The distribution can be in polynomial form. This is an example of device degree distribution. The proportion of devices sending 5 coded segments is quarter. I'm going to describe the iterative decoding processing between these two SICs. In the intro slice slot SIC, for example, at the second slice slot, even if there exists an interference from device 9, the segment from device 3 is decoded successfully. At the sixth slice slot, the segment from device 3 is also decoded successfully. In the inter-slice slot SIC, due to MDS code, all the 5 segments can be recovered. Therefore, the 5 segments are removed. This processing is repeated until no segments can be removed. The performance metric of the system is average normalized offer traffic G, which is the number of correctly received packets per slot. Optimization of distribution provides maximum G. We are interested in asymptotic performance of the traffic G. It is shown that the threshold value of G exists. Resembling the decoding analysis of LDPC code, the belief propagation threshold can be obtained by iterative decoding. It is achievable in practical. Map decoding maximizes the posteriori probability of each packet and given map threshold. The map threshold is the highest performance when not addressing the complexity of decoding and is the upper limit of practical decoding such as the BP threshold. Converse band expresses an impossible threshold to be approached and is tight if the map or BP threshold are close to the band. In previous works, BP threshold and converse band were derived over various channel model. Also, map threshold was approximated over collision channel model. However, they are unknown over Rayleigh channel. In this presentation, we derive BP and map thresholds and converse band for the coded slotted ALOHA system over Rayleigh block channel. I'm going to give the density evolutions equation of coded slotted ALOHA system over Rayleigh channel. The two equations plays a key role in our derivations of the threshold and the bound. The upper part is a graph representation of coded slotted ALOHA. We treated the activation probability pi as the erasure probability of binary erasure channel in the context of LDPC code. When the number of slots approaches infinite, the bipartite graph becomes protograph with degree distribution rho and lambda. Notation P is the average probability that a message is erasure from a device node group to a slice slot node group. Notation Q is the average probability from a slice slot node group to a device node group. The small l is the iteration index. Similar to LDPC decoding, we have the two iterative equations for the coded slotted ALOHA. Probability of P depends on degree distribution lambda and segment-oriented code. Function f is the probability that among the other nu-1 incoming message to the device node, at most k-1 segments are successfully recovered. The MDS decoding gives the probability. When a repetition code is applied to a segment code, it is referred to as irregular repetition slotted ALOHA. Function the probability of Q depends on degree distribution rho, the channel-oriented code, and channel phasing. Function chi has the expression of this. Here, epsilon is the error probability of decoding M collision within a slice slot of a fading channel. In particular, this equation is derived for Rayleigh fading channel model. For practical reasons, we consider kappa max decoding. We use a finite number of kappa instead of infinite here. The kappa max decoding means that the intra-slice slot SIC is carried out only when the number of collisions is equal or less than a given constant kappa. Now, let's turn to the derivation of coded slotted ALOHA. We realize the density evolutions equation here by removing the iteration index and do the two curves of the two functions. As you know, a necessary condition for successful decoding is to have an open tunnel between the two curves. The tunnel guarantees P and Q approach to very small value. We calculate the integrals of two functions to commute the two areas below two curves. The open tunnel means that the sum of the two areas is smaller than the entire domain. After some manipulation, we have the equations here. The solution of the equation gives the converse band. Next, let's turn to the derivations of map threshold. In this figure, we have the Tanner graph of slotted ALOHA. Now, we have randomly connect edges to inactive devices. The resulting Tanner graph becomes almost identical to the Tanner graph of LDPC code of a binary erasure channel. In other words, pi is treated as the erasure probability. This bridge between the LDPC code and slotted ALOHA schemes makes it possible to derive the map threshold for the traffic. Then, BP exit function is given in parametric form. Until BP threshold, the BP exit function remains at 0, and beyond the BP threshold, it jumps to the value of the average packet loss rate. On the other hand, map exit function is defined to convergence to 0 when pi is less than map threshold, and to coincide with the BP exit function when pi is greater than map threshold. In context LDPC codes, the integral the curve is called trial entropy. The gray area is derived by subtracting the integral from 0 to map threshold from integral over the range 0 to 1. Using trial entropy, it can be calculated by substituting x bar into the trial entropy. Identify the activation probability at which the area from 1 to the activation probability equals p of x bar. Finally, map threshold of traffic is obtained by multiplying by the constant alpha. We obtain the map threshold for the irregular repetition slotted ALOHA. It is an open problem to find the map threshold for the coded slotted ALOHA. I present some numerical result. The numerical analysis parameter as shown in this table. The blue dashed curve is the numerical results of BP threshold. Before segment-oriented encoding, each message of devices was partitioned to two message segments. The simulation result of 10,000 slots confirms the asymptotic result. The threshold of two segments case is higher than that of the single segment case. The converse band and the map threshold are here. The map threshold is obtained in the case of the single segment. This figure shows map thresholds and converse band. Our converse band are tight in the sense that the map thresholds are close to the bound. We also propose the derivation of BP threshold with spatially coupled slotted ALOHA over Rayleigh channels. We show the numerical result here. BP decoding threshold achieves map threshold and is close to the tight converse band. It is called the threshold saturation effect in the LDPC context. Finally, I will summarize my presentation. We derive BP and map thresholds and converse band for coded slotted ALOHA system over Rayleigh channel. Our numerical results show the map MDS coding provides higher BP threshold than repetition coding, and the spatially coupled scheme achieves map threshold. Moreover, our converse band are tight. Thank you for your attention.